Hey guys, welcome to lesson 7.1, where we start discussing confidence intervals. So what is a confidence interval? When you collect some data, you will get some sort of single number from a sample. So for example, if you're looking for a proportion of a population, you will get a sample proportion. So like a sample proportion or a sample mean. Now, the sample data, that number that you get, is almost certainly not the same as the population value, the population parameter. So if you have a sample of, let's say, 100 freshmen, and you find the average weight, then if you were to look at the population of all the freshmen at a university, the average weight of those 100 is almost certainly not going to be the same as the average weight of the whole population. So different random samples give different point estimates. That makes sense. If you took 100 different freshmen, you will almost certainly get a different average. And none of them lands exactly on the truth. So if I wanted to know the average of the whole population, that would be the parameter. So different samples have different answers. For example, cars on campus. How many students have a car on campus? In the first sample, 24 out of 400 do. In the second sample, 22 out of 400 do. So you have a p-hat, which is a sample proportion. In the first one, you have 60%, and in the second, you have 55%. So just basic variability between samples. Hours of sleep, you interview 12 students. In the first sample, they averaged 7 hours with a standard deviation of 0.93 hours, and the second they averaged 6.5 with a standard deviation of 8.5. Again, it makes sense. Different samples from a population give you different sort of sample statistics. Now, a confidence interval takes that point estimate, like the average of a sample or a proportion of a sample, and then does a plus or minus margin of error. So we say, all right, so we're going to start at my sample statistic. We're going to go a little bit to the left of it and a little bit to the right of it. So the margin of error is the multiplier times the standard error. And we'll talk more about how to construct these, but the general idea is start with a sample, get a sample statistic, and then go a little bit to the left of it, a little bit to the right of it, depending on the confidence level. So population parameter, we don't know it. If we did, then we wouldn't have to do a confidence interval. Population parameter is to P is the population proportion, mu is the sample mean. For a sample statistic, it is computed and it varies depending on the sample. P-hat is the sample proportion, X bar is the sample mean. And the point estimate is we build from it. So start with a point estimate, go to the left, go to the right. And we're trying to capture the population parameter. So for example, the Hokie Passport dining poll, random sample of 400 students, 256 are satisfied. So in that sample, my sample statistic is denoted by p-hat, we have 64% of students that are satisfied. Now the reported margin of error is plus or minus 5%. So my interval would be 0.64 plus or minus 5%. So between 59 and 69%. And we would say we're 95% confident the proportion of all VT students satisfied with the dining options is between 59 and 69%. So the idea is start with the point estimate that comes from the sample, and you go a little bit to the left, a little bit to the right. That distance that you go left and right is going to depend on a number of things. It's going to depend on the size of the sample, and it's going to depend on the confidence level. So the higher the confidence, the wider it's going to be. What does 95% confident mean? So imagine every possible random sample of 400 students. Each sample gives a different p-hat and a different interval. Now the idea is that 95% of all those intervals are actually going to contain the true proportion of all students that are satisfied. So if we were to take a census and find the proportion of all the students that are satisfied, it would take a long time and it would be expensive. This is why we do sampling. But that true value exists. And 95% of our samples, the way we set them up, would actually contain that value. So that also means if 95% capture it, that means 5% miss it. The confidence level describes the procedure, not any single interval. So the idea is 95% confident means that if we were to do it again and again and again and again, now we wouldn't, we're just going to find one sample. But in theory, if we were to do it, 95% of intervals would contain it. So here's a graphical interpretation of that. Here is the true population proportion right down here. And then you have 25 different samples, each of them represented by a line. Notice this sample contains it, contains it, contains it, contains it. And some of the sample, the way they're set up, will miss. Right? So this idea is that we are 95% confident. So 23 of 25 capture it, 2 miss. The ones that miss are right here. And the idea is that if we were to do like 100 samples, then we would expect 5 of them to miss just by the way things are set up. And that's due to sampling variability. So the correct thing to say is we're 95% confident that the proportion of all VT students satisfied with the dining options is between 59 and 69%. We don't want to say there's a 95% probability that P is between 59 and 69%. So P is a fixed number. The interval either contains it or doesn't. The probability is left. So we just talk about our level of confidence. So we'll say like we're 90% confident or we're 95% confident or whatever percentage confident in our interval containing the actual parameter. Now, a couple of things. As you increase the confidence level, the interval widens. So as confidence level goes up, so does the length of the interval. And the idea is, if I want to be extremely confident, I want to give you a wide interval. So if I want to talk about, for example, how confident I am in the temperature tomorrow, as I increase my level of confidence, the range that I give you for possible temperature for tomorrow is going to grow, which makes sense, right? Because I want to make sure my interval contains the actual temperature for tomorrow. The other way to talk about the size of the interval is the bigger the sample size, the smaller the confidence interval. So as my sample size increases, the sample statistic is more likely to be closer to the population parameter. So bigger samples mean that I can shrink my interval and still be pretty confident in my interval containing the population parameter. So same point estimate, same confidence level. More data means smaller standard error, which means I can have a tighter interval. Again, it kind of intuitively should make sense that the more data I have, the more close I can pinpoint the correct number, and I don't have to go as far to the left and as far to the right. Variability, more variability among individuals, larger standard error, wider interval. So if my sample is kind of all over the place, then my confidence interval is going to have to be bigger to account for that. If my sample is like a pretty close pattern, then I don't have to go as wide on average on the intervals. All right, so let's look at this example. A poll reports that 64% of a sample with a margin of error of 0.05 state the confidence interval. So 0.64 plus or minus 0.05 gives me an interval of 0.59 to 0.69. Interpret the interval in one complete sentence in the context. So we're 95% confident. Let me see. Doesn't tell us the, I think we're using 95% confidence level. So we would say we're 95% confident that the interval between 59 and 69 contains my parameter. Classmate says there's a 95% probability that P is between 0.59 and 0.69. What's wrong with the statement? So P is fixed, so there's not really a probability of where it's at. It's 100% where it's at. Many samples, suppose 200 different random samples each produce a 90% confidence interval for the same proportion. How many of those 200 intervals should capture the true value? All right, so if I have a 90% confidence interval and I have 200 different samples, I'd expect 180, which is 90% of 200, to capture the population proportion. Okay. So key terms, point estimate is the one number from a sample standing in for the parameter. Confidence interval is a range of plausible values. Margin of error is the difference on each side of the point estimate. So I have a point estimate, and then I go to the left of it, to the right of it, and that distance that I go to the left and to the right, that's the margin of error. Multiplier set by confidence interval scales the standard error. We'll talk more about that in the next two sections. And the confidence level is the long run percentage. So as I do it again and again and again, it's the percentage of all samples. It's the percentage of all confidence intervals constructed from samples that capture the population parameter. So point estimates vary from sample to sample. One number is never exactly right. Every interval is point estimate plus or minus the margin of error. 95% confident describes the procedure. 95% of all sample intervals capture the parameter. And the confidence level widens the interval. So the higher the confidence level, the wider the interval. Sample size shrinks it. The bigger the sample size, the smaller the interval, all else being equal. So that's the introduction to confidence interval. And in the next two sections, we're actually going to go through the mathematics of calculating them.